taking you behind the scenes of the National Institute for Data Science and Artificial Intelligence.
With unprecedented access to the scientists pushing boundaries and shaping our future, this show will take you to the cutting edge and beyond.
And whether you're an expert yourself or just science curious, this is the show for you.
Welcome to the Turing Podcast.
Hello everyone and welcome back to the Turing Podcast. Today we are joined by Dr. Chris Hicks and Dr. Vasilios Mavroudis, who co-lead the AI for Cyber Defense Research Centre at the Alan Turing Institute, which aims to solve computer security and privacy problems using autonomous decision-making. Chris and Vaz, welcome to the podcast.
Nice to be here.
Great. Well, firstly, tell us a bit about your background and journey to leading the AICD group at Turing.
Chris, do you want to go first?
Sure. It's quite a similar story, actually. So I joined the Turing 4 years ago, initially looking at trustworthy digital identity, privacy-enhancing technologies, but I'd always kind of had this really keen interest in machine learning for cybersecurity. I met Vas on that project, and we started thinking quite a lot about reinforcement learning. It's kind of quite a different paradigm in machine learning. And it all started to make sense, right? So within that paradigm, a lot of the security privacy problems that we were used to thinking about seemed a lot more amenable to machine learning, seemed like we could do some really interesting stuff. So I think probably 2.5, 3 years ago now, we applied for a small grant to look at that in more detail for about a year, half of our time. So we were 0.5 FTE on reinforcement learning for security for a year. During that time, we put together a team and won our first Cage challenge.
Which has been featured on the podcast before. That was Kate and Miles, right?
Yeah, both of them brilliant researchers. We still work with Miles quite closely. Sadly, Kate's moved on now. But yeah, so and then since then it was kind of just a rocket ship really. Once we went, that kind of put us on the map. One of the funders actually came to us afterwards and said, "You need to keep these people around. We'd really like to see this turn into something larger." We wrote the kind of proposal for what's now the AICD Research Centre, and here we are. Probably I think 18 months, maybe getting on for 2 years now from when we launched.
Nice. And I guess I'll go to Vaz in a minute, but what was your sort of research background before you got into all this? What was your route to cybersecurity and machine learning?
I did a computer security PhD at the University of Birmingham. So I was mostly looking actually at embedded systems in cars. So did some reverse engineering, cryptanalysis of immobilizer systems, and then looked at protocols for enhancing privacy of broadcast authentication. So you have some kind of interesting and slightly kind of paradoxical privacy problems whereby you want cars to shout all the time about where they are, where they're headed, and at the same time not protect the privacy. Yeah, exactly. So you can kind of spend forever thinking about ways to improve that and trade things off.
Awesome. Very important area of research. Vaz, what about you? What's your background? How did you come into the world of cybersecurity and ML?
Yeah, I don't know if that's the case anymore, but I started doing system security, which means hacking, basically, a long time ago.
But you're one of the good hackers, right?
Yeah, I mean, people associate hacking with accessing systems without authorization, but in practice, all it means, or at least what most people do, is just use software and hardware in ways that's not intended by the designers. So I started doing that a long time ago, just because I was interested. And then I just kept finding ways to keep doing more of that. So this led me doing a computer science degree, and then a master's in information security, and then a PhD on computer security and machine learning. And that's how I, as Chris described earlier, I gradually started realizing that through machine learning, we could solve many of the problems we were facing in computer security.
Nice. I mean, it all sounds really interesting, but one question that Anneca and I had before we started recording was like, what actually are the big risks in cybersecurity at the moment? I mean, are there too many of them to name? Think of like the Turing podcast listeners' point of view. I mean, we've all heard like scare stories. We also had our neighbours in the British Library had a big hack. So yeah, like what are the big risks at the moment?
I should have probably prepped for this question, but I didn't. So I can't promise this is gonna be a comprehensive list with exhaustively include all the threats. I think malware remains one of the top threats, and the malicious actors are advancing towards more sophisticated techniques, and this is an arms race that has been going on for a very long time.
So malware is like just any software that does bad stuff on your computer?
Yes, and lately, in the last 5 years, ransomware has become a really prominent type of malware in which, to put it simply, malicious actors use malicious software to encrypt your data and transfer them to their own premises, and then in many cases blackmail.
Extortion.
Yeah. About sharing your data in an unauthorized way with, or selling them even on the black market.
Yeah. I mean, that sounds really bad. And yeah, we've certainly heard in the news some stories like that. So what are the kind of problems that you're in particular looking to solve with your group, with the AI for cyber defense?
So I think in general, we've kind of got a broad vision, which is a kind of a paradigm shift in security. So we really think that these autonomous decision-making algorithms, deep reinforcement learning, and how they intersect more recently with kind of transformer models, large language models, does represent a fundamental change in the way that security research might be done.
Right.
So I think we like to think that a lot of the research that we do is super scientific. And I think that it is in kind of the evaluation, but often the way that people discover, for example, vulnerabilities in systems is not massively scientific. It's very much a kind of process of trial and error. There's a lot of intuition. There's not really like a great rule book out there for how to find vulnerabilities.
I mean, is it a lot of the case you find vulnerabilities in computer systems when something bad happens, or are you talking more about people in a systematic way looking for problems before they occur in the real world?
Yeah, exactly. I guess flipping it round, it's how can we provide assurances that systems are secure? And there is work there, but I think that the work that we're doing, broadly speaking, aims to provide new ways to automate the discovery of those kinds of vulnerabilities and perhaps find novel strategies for defending systems.
Okay, that's interesting. So yeah, it's about discovering problems as well as fixing them.
Yeah, that's always been a really big part of security.
Right.
Yeah, if I can add, one of the rules of thumb that I use is when there is a task where you can't explain as a human, you can't explain exactly what it is that you're doing and you're relying on your intuition. This is an area where you could possibly use machine learning to do what you do and maybe even better. In the cybersecurity world, we're lucky in that we have a lot of data from both systems and human analysts from lots of years. We've been doing this for a long time, not us personally only, but as a community.
As in cybersecurity has been a thing for a long time, yeah.
So if we could use this expertise to train algorithms to do what we're doing, we could get, as defenders, a step ahead.
So that's interesting. Are you saying that a lot of what cybersecurity analysts do is sort of not like easily like written down, but they have rules of thumb, they have experience that it's hard to write a traditional computer program, so maybe machine learning is the answer.
Exactly. There's nothing magic going on there. There is a thinking process. We might not be able to explain what it is that we're doing, but an algorithm might be able to learn the same thing and do it more efficiently.
I think it's worth emphasizing as well, because Vas is saying machine learning, and that includes reinforcement learning. But I think probably for the listener, and something that like not everyone realizes when we talk about this stuff, is that a large part of the kind of autonomous decision-making aspect to what we're describing is, if you've seen AlphaGo, right, it's this idea that you can get a computer system actually just by defining a reward or a goal to, with very, very few assumptions about the underlying system, learn a strategy for doing well. So in essence, with AlphaGo, they got a computer to play itself at Go, billions of times. And in doing so, it became incredibly good at playing Go, where the reward or the goal was to win the game. Mm. And we're kind of doing analogous work in security, where we're defining objectives such as, in the offensive space, perhaps inducing a denial of service attack against a target server. So that would look like...
Yeah, what is a denial of service attack?
So denial of service attack, broadly speaking, is where an adversary denies service to the target's resource or service.
So if it's like a website, making the website crash.
Yeah, exactly. And conventionally how that was done was the sort of DDoS, which listeners might have heard of, is a distributed denial of service attack, whereby you simply overwhelm the resources of the target.
Right.
So, if my website normally gets 1,000 visits an hour and I throw 1 million visits at it, if it's not set up right, it will probably crash, and that will deprive real users of the opportunity to visit their website. What we've looked at is, just one of the pieces of work specifically is doing that using something called GraphQL, but basically you don't need to be distributed anymore. You can just send a single query to a server. And if you form that query in the right way, you can induce a denial of service by essentially consuming all the compute resources on the target. But framing that as a game, the reward would be to increase the response time from the server to be as long as possible. Mm-hmm. And you can actually find a gradient there to optimize. So you play this game just as you might play Go, whereby I'm going to get rewarded for making the server really, really slow.
So at the moment, it sounds like the game is to do the cyber attack.
Well, in that instance, we have also, we mentioned the cage challenge. We do also do a lot of the defensive stuff. They really go hand in hand.
Right.
Defense is generally more difficult.
Mm. So I think what you've just described there is like, you imagine you want to train some defender AI for this cybersecurity purpose of defending against a denial of service attack. But to be able to do that, you also want to have some way of simulating the denial of service attack. And that's why you've also used a similar kind of AI, or in other words, well, more specifically, your reinforcement learning system to do that. Is that correct?
Yeah, it's an established premise in security that offensive research helps with defense because you find your flaws before the adversaries do.
I see.
And what's so compelling about this approach, which you're seeing not just with the work we're doing, but more broadly in the literature, is that traditionally to do this work, you needed very rare to find, very expensive hackers, in essence, to test your product to find the vulnerabilities.
Yeah.
What the techniques that we're developing and others are developing can do is bring that level of analysis of like products, servers, applications to a much wider audience, and to do so without requiring that expertise. So you're seeing academic work, at least, that enables people to like test their microcontrollers, for example, to check that they don't have a certain type of vulnerability in them, like a microarchitectural.
What's a microcontroller?
So it's kind of like a specific version of a CPU. That's probably not the best description in the world. So this was actually my undergraduate degree. It was joint honours, but it included some electronic engineering. And so a microcontroller is effectively a small processor, but it's designed for controlling a bunch of input-output.
Okay, like a remote control or something like that?
Yeah, or like your washing machine will have a microcontroller in it.
I see. So it's like okay, a really specific limited computer for doing one sort of thing, right?
Yeah.
Okay.
Yeah.
Okay, sorry. So I'll ask you what a microcontroller is now. Now back up to what what you were explaining before, if you can.
I think kind of in a nutshell, what's really cool is that small manufacturers, take the washing machine example, right? Say I'm a washing machine manufacturer.
So that is something that could be hacked, you know,
right? And
theory.
Well, these days, everything's connected to the internet, right? So my washing machine has got a smartphone app, and I want to have some assurances about the security of that, but I don't have an in-house expert security team.
Right.
These tools can essentially make access, like enable such manufacturers to actually test their product to a much
stress test
greater
them
degree.
If there's any vulnerabilities. Yeah. Well, that's really cool. Yeah, I guess maybe it's worth asking. You talked a little bit about already that it's using this reinforcement learning, and that it's reinforcement learning has been good in the context of games before. What led you to like that area of machine learning in the first place, as opposed to like other methods?
So reinforcement learning fits very naturally the cybersecurity paradigm, in which, as Chris said earlier, you, through trial and error, you probe a system and you increasingly learn more about it until you find the flaws or the security issues that are present. In comparison, supervised learning, which is the more classic machine learning and more developed area, it requires a data set with that is usually annotated as to what is what in there. And then the algorithm runs on this and learns from that data set. Whereas the reinforcement learning gets to interact with the system in our case, is given some tools, which might be penetration testing tools, hacking tools, and it gets to try actions and develop strategies through sequences of actions. So it fits more naturally. Having said that, we're using both, and it seems right now that supervised learning has a place in automated testing. It's just that reinforcement learning is better in planning. So most likely in the next few years, we're going to see solutions using a combination of both.
I'm imagining as well that with other kinds of machine learning, that the lack of like examples is a problem. And as you were just sort of saying, like the reinforcement learning agent having a system where it can explore sort of logically makes sense. Go on, Anneca.
As a resident layperson here, so I just wanted to understand. So we talk about the learning, but I'm wondering, what's the kind of goal? Is it to kind of combat these risks, or is the goal to kind of create a report, essentially to say, okay, this is what we've learned, and this is kind of how you can apply it to have a safer, whatever you're trying to create, if that makes sense, the washing machine, for example. I guess what kind of is the end goal with these tools, or what's the result?
So I guess, the result is a good word. So the result is a set of instructions that you can follow for achieving the goal. Like that's what the algorithm will give you. So if you're playing chess, it will give you a bunch of chess moves that it believes if you follow them, will kind of maximize your score in chess. I guess in the offensive case, what it will give you is a recipe for inducing the type of adversarial goal that you are interested in. That's often in the sort of...
it's like a simulation of the hack that people might do.
Yeah, and in the way that in the way that attack and defense go hand in hand in security, that generally is a stimulus for people to come up with more secure systems. So kind of back to the micro-architectural example, although we're still being kind of blighted by these things, most recently, the kind of Apple Silicon, actually, I think just last week. But sorry. Go on,
okay, tell us the example.
I guess the thing is, when that came out, it was probably 10 years ago now, micro-architectural side channel attacks. It was like mind-blowing, right? It was like every computer out there with an Intel processor suddenly wasn't secure anymore.
Right.
And it wasn't secure at like a really fundamental level of the system, the very hardware. And what that did, although it took a few years, was it really provided a stimulus for people to build more secure hardware platforms, although we're still a long way from something that's seriously secure. But so I think that's the hope on the offensive side. On the defensive side, I think the hope is that we come up with strategies that are able to defend computer networks and do so using only very weak assumptions about the adversary. So that means I'm going to assume they're already inside my system and they are attacking me. And what that might enable is for effective strategies like recipes, right? Steps you could take that allow you to mitigate the effect of an attack or the impact of it, maybe minimize the amount of your data that's encrypted in a ransomware attack. That could be rolled out to all of these kind of SMEs, small, schools, hospitals around the country that don't have, IT security experts on premises.
Those examples, would they not all be using, software and hardware from like big tech giants that do all of their cybersecurity and push updates anyway?
I mean, in practice, like the idea.
Is that too?
No, I mean the idea
optimistic.
The idea that manufacturers and vendors take responsibility for their products once they've sold them, I don't think holds up to reality. Like, I'm sure I've seen Windows XP screens on at least one point of sale device.
Right, and they obviously, Microsoft will say, because that's an older version, we're not going to continue developing security patches because, that's time and money for them. So, but that's sort of baked in as we'll stop doing that after a certain date. But then obviously in the real world, there might still be people using those systems.
And just briefly, I think like a good mitigation that so there is an issue, as you describe, with sort of, how do you actually, if the people who you're hoping to help are the people that take the fewest precautions, how can you induce them to actually embrace these kind of recipes that we produce? But NCSC's like Cyber Essentials is probably quite a good example, right? Where, if I'm not mistaken, my understanding is SMEs of a certain size, they have to meet a certain standard of sort of like hygiene best practices in cybersecurity, or they're at least encouraged to.
Right.
And that literally includes things like using two-factor authentication, making sure that passwords are, appropriate.
So it's sort of analogous to like the GDPR that we all have to do for data security. The IT departments of companies have to do this sort of like basic IT security up to a certain level.
Sure. And there are also really strong market incentives. So back to the ransomware example, you can, there is a very, very large pound sterling value we can put on the cost of these attacks to businesses. Don't have the numbers off the top of my head, but it was maybe like 60% of businesses or something in the last year were the victim of some sort of cyber attack or disruption. So I think I'm an optimist at heart. So I think it should be. I'm optimistic that we can have a real impact with this stuff.
Yeah. I mean, it's obvious that it's a huge problem and costs people money. And were you going to say something, Vas?
Yeah, I think we need to touch a little bit on responsible disclosure, which is again an established way of disclosing findings in cybersecurity research. This is not specific to cybersecurity research using machine learning, but rather, okay, you found a security flaw in a product used by people. What do you do next? 15 years
ago. Post it on Reddit? Or?
Yeah, exactly. That's exactly what you shouldn't do. So 15 years ago, things were not that well defined. So people would post it online, would go on, brag on whatever platform they were using. Vendors would go after people finding vulnerabilities. Now this whole process has changed a lot. So what you should do is you should reach out to the vendor and give them all the details of what you found. In many cases, there are bounties, so you might receive a monetary reward for your findings.
Right.
And the process has been
You might get given a job, I suppose, I guess.
I mean, absolutely. There are people who earn a living through that. That's their job. They just go around finding products and help fixing vulnerabilities. And it's a really very well working model, because as a vendor, you don't have to employ those people and you get to reward them only if they find something. And for these people, they're free to go and try different things.
Bug bounties, is it? What do you call them?
Yeah, bug bounties. Yes.
Right.
This process has been so streamlined now that there are very specific rules on how you compete. Sometimes you find something and it's doesn't qualify you for a reward.
I was going to say, if you send them like, oh, I found this really bad bug, here's how I fixed it, and they're just like, cool, we won't pay you any money, but thanks.
It happens sometimes. Usually vendors do honor the promise they've made, because then other people won't look into their products if they make a name for not paying. Overall, the incentives are there for people to responsibly disclose what their findings, and this includes also cybersecurity research. There is a risk associated with machine learning, which is, let's say AICD tomorrow comes up with a great algorithm model that finds tons of vulnerabilities. So you set it up on a system.
Great, you go collect those bounties, profit.
Yeah, that's great. But someone needs to fix all those things.
Right.
And now, until yesterday, we didn't know about any of those problems. So it was fine that people in the real world were using the products.
Sure.
But now the vendor knows, and they don't have the capacity to fix them all at once.
Right. And they can't fix them with an agent, with an AI.
That's a hope. This is obviously a hypothetical scenario, but maybe not that far-fetched.
Another layperson question. Do any of these tools kind of in some way quantify or measure the sort of severity of these issues? Like if, for example, if I was a vendor, how would I know, let's say I didn't have the funds, how would I know what to kind of target first?
I think there is a ranking that is very well established, and actually in bug bounties, vendors pay more for more critical vulnerabilities. So there is an ordering. So if you found 10 things and 2 of them were more critical, they may be resulting in data leakage, they would definitely go and fix these first.
Can you tell us a bit about backdoors in cybersecurity and maybe some of the work you've been doing around that with reinforcement learning?
Yes. So machine learning is great. It seems we can use it to improve the defenses of our networks and systems. The problem is we are also introducing a new component, which is now the machine learning model, which, as cybersecurity people know, every new component comes with new attacks. So this machine learning model could be attacked in and of itself. So
So just to clarify, so we're talking about like cybersecurity flaws in a piece of software that happens to be itself like a machine learning model.
Exactly. So backdoors are one type of such flaws. There are others. You can think of a situation where you buy a product that uses machine learning or AI to defend your network. You put it on your network and it does a great job. But backdoors work in the following way. Maybe there is a rogue employee in the vendor selling you the AI. And what they do is they embed, it's really not that difficult, embed a hidden trigger in there. So when this defender sees a specific sequence, more like a secret knock on the door, it does open the door for the adversary, or it doesn't do its job.
Okay, yeah. So I guess normally, I think, if I understand correctly, like a backdoor in the program is like something which you didn't expect to be there, or is it always something that's intended to be there? Like
it's not intended to be there, unless if you're talking for the adversary who puts it there.
Right.
And the problem is because of how deep neural networks work, there is no explainability. So even if you audit the product or the model, it's really hard to know exactly what's encoded in the neurons.
So just before we sort of go into the why it's different in the machine learning model case, what's the difference between a backdoor and just like any sort of vulnerability in a computer program? So
it's the intent. So someone, not necessarily for adversarial reasons. So I think you picked up on the fact that backdoors aren't just a phenomena of machine learning systems.
Yeah.
And actually, one of my colleagues, when I was doing my PhD, they spent their whole PhD automating the discovery of backdoors in firmware for embedded systems. So there's a washing machine that's connected to the internet.
Right.
One kind of backdoor is that what they intended was for developers during the product development to have a really quick way to get very privileged access so that they could debug it during development.
Sure.
And sometimes that doesn't get switched off.
Right.
And the kind of security of that backdoor rests at that point only on it being unknown to the general public.
Right.
But it's just lying there. There are, of course, as Vas describes, not only machine learning systems, but in general, kind of backdoors that were put there more deliberately by an adversary.
Right.
So it's intent as opposed to a vulnerability, which typically is an accident.
I see.
The designer wanted a secure system, or at least didn't intend an insecure system.
And so, so going back to the machine learning models then, so you talked a bit about how the fact that we don't really understand how they work means that if there is a backdoor, how could you possibly find it?
So this is the problem with AI-enabled defense. As an attacker, if you're using models, if they work, fine. As a defender, because you want to make sure they are reliable, you need to have some form of warranties. And right now, we get it in the form of auditing how a system we've deployed works. And with traditional systems, they're just programs. You can read the code and you know what they do. With machine learning models, the training process is easy to understand. It looks at the data, or it interacts with the environment, it learns. But what exactly it is that it's learning, there's no very good way of knowing.
Yeah, so in this case, there are like 3 different kinds of AI that we could potentially not understand how they're working, which is the piece of software that might be being attacked, which might be an AI machine learning model that might have a backdoor in intentionally or otherwise, an attacking piece of software, which could be also an AI, which you've built to test vulnerabilities, but then you might not understand how it does its job exactly. And then also your defender AI, which also might successfully defend, but then you might not know how it works. Is that right?
And all 3 of those could have backdoors in them.
Right. Backdoors within things designed to catch backdoors. It's complicated.
Yeah, I don't know if this is going to make you feel any better, but with regards to the attacker AI, maybe it doesn't scan the whole attack surface, like the whole scope of possible attacks perfectly, but this is not that different from what we're doing right now. Security today is a best effort process. We, as community, again, we're very good at it, but we're also surprised relatively frequently by new findings. So this hasn't changed.
Do you feel like you're in a bit of a Wild West situation at the moment with this kind of? Is there a lot of like new kinds of attacks to defend against and stuff like coming out of the real world?
Not yet, but this risk is coming closer. I don't think we've reached yet the level of planning and kind of attack orchestration required by models to be effective in the real world. There was a report published by a large AI vendor recently, and they tested their best models for this exact kind of attacks, and they weren't there yet, but they could do simpler attacks, which hints that it's getting there. Their forecast was 2028 or 2030.
Right. What for AI-enabled cyber attacks being a big problem?
But fully autonomous.
Fully autonomous. Well, that's Chris is shaking his head.
I don't know. I feel like that's pessimistic. It depends what we're talking about as well. You know, these things are at different levels. I don't know what, and it's really hard to, because it's not like the defense will remain stationary until 2030.
No, yeah, sure. I mean, you're already thinking about it, right? So
there are real world vulnerabilities with CVEs, which is the Common Vulnerability Enumeration. It's like a standard worldwide database of known vulnerabilities in systems. There are real world CVEs that have been found by deep reinforcement learning agents already.
Yeah.
So this stuff is finding real world vulnerabilities. It's just doing so with quite a narrow scope.
So you're saying that there's a database online of across like commonly used computer systems, vulnerabilities that have been reported and that are known. And when you're using this reinforcement learning like attacker, they are independently finding the same kinds of vulnerabilities, which is a sign that it works.
Yeah, and not only that, but that are novel. CVEs, not loads, but maybe a dozen.
Yeah, might find some
that were not previously found by humans.
Right.
And were found for the first time by deep reinforcement learning agents.
Interesting. Well, how pessimistic are you, Vas, about? Well, I guess there's two things here. First is just like the idea of like a malicious human actor deploying sort of cyber attacks in a way that's bad, like a level that we haven't seen before, because it's using an autonomous AI. And then I guess the second question is, what about super intelligent AI doing this kind of stuff? Do you worry about that?
I'm actually very optimistic. I consider the highest risk being the transition period, in which the access to defense models and attack models, perhaps it might not be entirely symmetric. At some point, this is going to kind of normalize, and we're going to reach a new equilibrium as we have right now. And maybe even end up with really, really robust software that doesn't have a lot of flaws to find in the first place. But getting there, it might be a painful process, and there might be years or a few months where we'll have to run after new findings all the time and try to patch them as quickly as possible.
I guess the thing you said earlier that made me optimistic is that realistically at the moment, businesses or like hospitals or schools or whatever that have IT systems can't, they don't necessarily have the staff, like cybersecurity personnel, to do these things at the moment, but to do defense properly at the moment. But then if you have this suite of reinforcement learning based defense tools, which they can just use to automate that potentially means more people or more businesses and more organizations being able to defend themselves.
Yeah, I totally agree. And it's one of our goals with AICD, essentially democratize cyber defense. You have SMEs that cannot afford and even a team doing IT, let alone a cybersecurity expert. So if we had something that gets the basics right, I would go a long way.
A potential source for optimism as well, in terms of the sort of attacker-defender balance, is that potentially finding these strategies could be very computationally expensive, in the way that we've seen the training of large language models be very computationally expensive. What that might mean is that they're not accessible to small groups of attackers.
Though what we seem to be seeing with some language models, so maybe it will be the case with these models, is they're being released openly anyway, or freely available online. So would you anticipate, or at least, as a paid software that's like an antivirus software now?
But I guess there's a difference between having the model and being able to use it for inference.
Sure. And
being able to train the model.
Yeah.
And in this case, I guess specifically, just to be clear, what would be bad is in this way that I talked about Go being trained a self-play, right, competitively. It would be bad if lots of attackers had access to systems that could find really, really good offensive strategies in the same way as we're searching for the defensive ones.
I see.
But it might be that the computational constraints around training these systems do actually create a sort of barrier to entry.
But do the small businesses need to be doing that, or can they just accept the trained models and just use them like any other? That was my example of the antivirus software.
Yeah. So that's exactly it. So hopefully it will be sufficient they may even not need the model. It may just be that the strategies themselves are valuable.
Well, talking about language models, how do language models factor into cybersecurities and this domain?
We've used them for a number of things. We had good results so far, and I think we can do even more. I am aware of several groups working on this, and I think right now in cybersecurity, everyone is trying to shoehorn a language model into every possible problem and see what sticks, really.
Yeah.
So some positive results we had so far is using language models to evaluate high-level security designs for privacy or other properties. And it seems to be doing better than what a human analyst would do, and much faster, if you believe it. And the other thing we are very excited about is using language models to build a cybersecurity context where you fuse information sources from different software services system all in one, that then you can feed into an RL model and possibly help it take the right decisions and have good situational awareness.
Okay, so what? Yeah, when you say situational awareness, what do you mean there?
So unfortunately, what happens is usually, let's think of a computer network. It can be very heterogeneous. You have laptops from different manufacturers, different operating systems, people's personal devices, and then you have some production servers maybe. All these systems produce log files, alerts, all sorts of things. The problem is making sense of all this within all this noise of what's going on in the network.
I see. So if you're the reinforcement learning agent who's like defending, this is all the like messy data that's being given and it's trying to figure out like how to do stuff with.
Exactly.
And if I'm right, what you're saying is the language model sort of can find a way to contextualize that data.
Exactly.
Cool.
I think as well, like one of the biggest limitations of reinforcement learning is its ability to generalize. So, that world-class Go agent that you've trained, if I made a version of Go that had one extra square in each dimension, would be utterly terrible at playing that game. It would need to be retrained. Whereas language models are quite good.
Yeah, that's. I mean, so just to clarify, I think like the sort of the algorithm itself can be applied to different contexts, but it has to relearn the new context, right?
Yeah.
Whereas what you're saying is language models can already do different. You can throw different ideas at it, different situations.
Yeah, exactly. So I'd be tempted to measure generalization in that specific context in terms of how much less training do I need to do than the amount of training to completely train from scratch for the new game, which may be zero. Maybe that essentially I need to completely retrain. And if I'm really good at generalizing, I hardly need to do anything. Maybe I can fuse shot or something.
Yeah.
Language models are very good at that. So I think we're quite hopeful as well at combining the strengths of both and looking to do work in the intersection.
Well, before we wrap up, maybe you can tell us what you guys think the future holds for this field. Before I come to you, I'm going to ask Anneca a quick question. Like, how worried do you feel after this conversation about the world of cybersecurity?
I feel, I don't know. Of course, I feel more worried because there are a lot more risks than I was initially aware of. But knowing that there's potential solutions, and that these kind of situations are being explored, and we're kind of looking at defense, but we're also looking at essentially kind of very, what's a good way of putting it?
Like the simulated attacks.
Exactly. I was going to say a very intense sort of know thy enemy, understanding of, what the adversary is planning. So although I'm worried, there's also a lot happening on the contrary to kind of make me feel a bit more reassured.
Yeah, I think it's really cool that like you guys are doing this research, and one of my colleagues, I can't even remember who now, once described the two of you as, quote, the rock stars of the Alan Turing Institute. So you can take that praise. But no, it's cool that we're doing this kind of work here at the Turing. But yeah, back to the question, like what do you guys think the future holds? Where is this all headed? Bit of a big question, sorry.
Can jump in with some. I mean, I'm really excited. I think what I hope is that it kind of circles back to the beginning of the conversation as well. What I hope is that we can automate a lot of the human trial and error that currently goes into the kind of attack defense, playbooks and security. And that in doing so, we'll actually gain a much deeper understanding of security and what secure systems look like.
Cool. Any thoughts, Vas?
Yeah, I had some more time to think while Chris was talking. So we started, you asked me early on how I started in security. And I said, well, I was just hacking, trying things, nothing illegal.
Just to clarify.
I have to say that security have over the years followed a very incremental approach, which works obviously, but it's also not that exciting. With AI, things are getting exciting again.
Cool.
Things are changing fast.
Hey, well, thank you both for coming. Just another quick question for you. How can our listeners hear more about the work you're doing with AICD?
Is it turing.ac.uk/AICD? That's our kind of research centre page.
That's not too many letters. Yeah, people can find that. It's quite a short, sweet URL.
I'm sure if you Google Turing AICD as well, it'll pop up, and we've got our latest publications on there and some more detail as well.
Fantastic.
Are you both on social media, or do you not use that for work?
We do, yes.
Which ones?
Most of them.
Yeah, both. We're both on Twitter,
LinkedIn.
We've
got a Google group you can sign up to.
We do for hardcore cybersecurity people or hardcore enthusiasts. There is a mailing list.
Oh, how can people find that?
We have a link on our website.
Okay, perfect. All right, Chris and Vas, thanks very much for coming on the podcast.
Thank you both. It's been a pleasure.
Great having you. Thanks.
Thanks for listening to this week's episode. The show is hosted by me, B. Costa Gomez, Ed Calstri, Joe Dungate, Christina Last, and Anneca York. Music for this podcast is produced by Jam and Sun. You can listen and follow via the link in the description or by searching Jam and Sun on Instagram.